Thank you for the invitation. So the title is Finding and Investigating the Brightest Galaxies at Redshift Greater than 3. So why do we want to find lenses, and why they're so valuable? Well, the problem is that even at the resolution of HST and JWST, you're basically, once you get to redshifts above 1, you're basically seeing details down to about 1 kiloparsec, not anything smaller than that. And if you look at the galaxy, it will be like a typical galaxy will be like a few pixels across. You're not really seeing any internal structure with unlensed field galaxies with HST, not much for most of them. With JWST, you might get a little bit better, but if you have a lensed galaxy like this, with JWST, you can see structures down to about 100 parsecs. So the typical magnification you get when you have galaxy lensed by a cluster is a few tens, basically. So then you can start seeing these individual clumps, which are not necessarily individual star clusters, but more like star-forming complexes, like 30 Dorados here. And really, instead of being in a situation where you're really, when you do imaging and spectroscopy, you're really collecting information from various environments with different stellar ages, different metallicities, and so on. So it's hard to interpret, whereas here you can actually see stellar regions, stellar clumps, which were formed at the same time with the same age. So I'm going to tell you, if you want to see something clearer, you actually need to look further away. And that sounds a bit counterintuitive, at least until you get of a certain age, and then you start to realize you need reading glasses, and then you have to put your book further away to see it clearly. So the situation here, shown here, is this is actually a local galaxy, Haro 11. It's quite famous as the first where people were actually able to measure directly ionizing radiation leaking from the galaxy. So this is UV radiation with wavelengths less than 912 angstroms, able to ionize hydrogen. So this was detected first with the IUE and then later with HST. So this is an HST image, and this is a reconstructed image of the galaxy I showed you in the title slide. And these are reproduced shown at approximately the same physical scale. So this is at redshift 0.02, and this is at redshift 2.36. So lensing here is doing the work for us, magnifying things that are really far away. So if we want to study this ionizing radiation, we actually don't know which of these clumps is producing that radiation, because this circle shows the resolution of HST and COS, which is the sharpest we can get at those wavelengths. Whereas once it gets redshifted, we can actually get a resolution like you see here, and this is actually a clump which is also leaking ionizing radiation. So we can see things sharper, actually, at certain wavelengths, intrinsic wavelengths, at cosmological distance. And of course, if this is at redshift 2, at redshift 3, we don't actually have to use HST to detect the ionizing flux. At that point, it actually gets redshifted into the optical region, not longer in the UV. So going back like 15 years. We started the project using the NOT to confirm candidate gravitational lenses detected in the Sloan Giant Arc Survey, detected in the Sloan Digital Sky Survey. So we called it the Sloan Giant Arc Survey. So the idea was that in Sloan, we could see these candidates, but we weren't quite sure if they were real lenses, so we did deeper and sharper imaging. So Moscow was a really good tool for that. It was very blue sensitive compared to other instruments, and it was on La Palma, so image quality was good. So we confirmed 217 lenses, and these were at redshifts mostly between 1 and 3, so-called cosmic noon, where most of the most vigorous star formation took place in the universe. So what you see here are blue things. It's rest frame UV radiation, basically, from young stars. Then we did it slightly different way of finding candidate lenses and got 62 more. And these have been used extensively for follow-up physical studies. This is actually from the front page of the NOT annual report in 2008. There are images from NOT, lenses found with NOT. And this one and another one, this one, is actually going to be observed in a few months, within a few months, with JWST. So they are part of an early release science program called Templates, along with 2 sub-millimeter selected galaxies, lens galaxies. Another thing we found serendipitously, which Johan and his students helped us with actually, was this lens quasar. So we found this, and then as we realized this was really interesting, it so happened that Johan was on La Palma with his students asking for interesting things to take spectra of, and we found an interesting thing for them to take a spectrum of, and realized that A, B, and C were actually the same source. And then with some more NOT observations, we found 3 more demagnified images, which we have monitored with NOT ever since. Gotten this light curve here of the 3 brightest images. So we have really good time delays, like less than 1% accuracy. So that was cool. And then people started finding, including us, finding more quasars lensed by clusters of galaxies, because those are really rare. So the next talk, you're going to hear about quasars lensed by individual galaxies, and those we know about 220 or more of. Whereas for quasars lensed by clusters, we only know about 7, basically, and 2 have not been published yet. So it's interesting because, well, I'm not going to say so much about it, but in the next talk, we're going to hear about, using time delays as an alternative way to measure H0. And I'm not going to say that this is better than necessarily than using individual galaxies as lenses, but they are prone to different types of systematics. So it's valuable to use both methods. So here's another of these systems that, oops. Okay, not good. Do this. Another lens quasar we have been monitoring for about 4 years or 4 seasons. So this is the A image. This is the B image, which is 2 years behind, and not working terribly well. This is the C image, which is 4 years behind the first. So pretty long time delays. You need a bit of patience. So that was some very brief highlights from the previous iteration using Sloan. But now there's a new survey available since a few years ago, the Legacy Survey, or Legacy Surveys. So that's a mix of imaging in the southern hemisphere using the 4-meter telescope at Cerro Tololo, and then combination of the 4-meter at Kitt Peak and a 2.3-meter in the north. So that's significantly deeper, especially in the Z-band, which means that you can see higher redshift sources and higher redshift lenses. So far, we found 1,500 good candidates. So the idea here is that because these images are sharper and deeper, you don't really need NOT imaging. That's not the most interesting or the most efficient use of NOT. It's better than to try to do spectroscopy of the brightest sources to actually measure their redshifts. So So here are the brightest ones we found so far. So these are actually the brightest known galaxies between redshift 3 and 4. So as I told you before, the ones we found before were between 1 and 3. This is between 3 and 4. And we're particularly selecting them just by selecting things that look green, because you basically have, in RZ, you have a rising slope towards shorter wavelengths, and then you have a break around Lyman alpha, which is in the R band. So R is brighter than GNC, so it looks green. And these are bright enough to do spectroscopy with NOT. So, and we also used, in the southern hemisphere, we used Magellan and VLT. So most of these are from this program. Yeah, actually. So, and a couple are from that previous program as well. So if you plot these with the R and Z magnitude versus redshift, you see that the new ones here are the ones which have the stronger colors, and the more faded ones, they are known previously. So it's basically, we're finding a sample which is as bright or brighter than anything known at that redshift. And if the galaxies are not lensed, they're fainter than this line here, basically. And if you look at the brightest, a selection of the brightest galaxies, which was studied from Sloan, basically, that's Megasaura and Cassowary. That's 2 samples selected from Sloan. You hardly have any above redshift 3, 4. So one of the interesting science goals here is to find out what kind of objects were responsible for ionizing the universe during reionization. And how did that radiation escape from galaxies? Because today, very little ionizing flux is able to emerge from galaxies. It's absorbed inside the galaxies. So the idea is to try to find Lyman continuum leakers at lower redshifts, because at these redshifts, at reionization, you cannot really study this radiation because it's absorbed along the way of sight. So the highest redshift you can hope to see this ionizing radiation is around redshift 4. So right now, at any redshift, there's only like 60 or so confirmed Lyman continuum leakers. So some of them are at pretty low redshifts, and some are redshift 2 to 4. And there's a puzzle, because if you look at samples of galaxies, try to measure the escape or upper limits for the escape of ionizing photons. You see that the upper limits are mostly below 10%, but you really need more than 10% to escape to be able to ionize the universe. So somehow there must have been some kind of rapid evolution from reionization, which is beyond the scale here at redshift 6.5 and higher, and these redshifts. So the escape fraction must have changed quite rapidly. So the idea is to find galaxies which have conditions similar to the ones in reionization and where you can see radiation actually escaping. And then maybe use those to calibrate other indirect measures of escaping radiation. And there are different alternatives here. You can look at the details in the Lyman alpha emission line. You can look at the emission flux ratio, 0.02 to 0.03, and the slope of the UV continuum. So again, if you want to do this, if you're looking at unlensed galaxies, you're measuring an integrated property of the galaxies, and there may be different regions responsible for, say, Lyman alpha emission versus O3 and O2 versus the continuum emission. You may be conflating different regions when you look at the integrated properties of the galaxy. So lensing is really a vital tool here to understand what's going on. So for instance, looking at the Lyman alpha can tell you quite a lot about escape, because if you have a scenario where there's a thin layer of hydrogen, but so thin that some of the ionizing radiation can escape, then typically Lyman alpha gets scattered a bit away from the systemic velocity. So we have a red peak and a blue peak in the emission line profile, but nothing at the exact wavelength of Lyman alpha. So the wavelength gets scattered away to the blue or red side, and then it can escape. Whereas you have other scenarios. So like this, for instance, if you have an ionized channel, you see this triple peak structure here. So you have the red and the blue peak from here, and then you have a central peak of Lyman alpha radiation escaping directly through a channel. And if Lyman alpha radiation can escape then directly, then we're certain that Lyman continuum radiation can also escape. Because the absorption cross-section of neutral hydrogen is it's 3 orders of magnitude smaller, actually, for Lyman continuum ionizing radiation. So this is the arc I showed you. It's called the sunburst arc. So that has a spectrum, telltale spectrum I showed you with a central peak. So the ionizing flux is escaping through it's a small gap in the clouds, if you gap in the which is cleared of neutral hydrogen. So to see this, you need a pretty high spectral resolution, like 4,700 in this case. And well, so spectral resolution is really, really valuable. It doesn't have to be more than about 2,000, but at that level. And then, again, if you look at different regions inside this sunburst arc with HST data, you can look at the individual clumps. So these are clumps where Lyman alpha continuum, where Lyman continuum radiation is escaping, and these clumps don't emit Lyman continuum radiation. So you see a strong difference in the O3 to O2 ratio and in the UV slope. So this is a way to distinguish them, right? If you can see locally inside a galaxy, distinct regions, characterize them. But if you saw this galaxy just as a small unlensed source, then you would observe this. So it would be unremarkable in the sense of these diagnostics. It would look like any other galaxy. It wouldn't shout out at you telling that this particular galaxy is emitting ionizing radiation. So that's just I was. So what would NTE bring to the table then concerning these diagnostics? Well, spectral resolution is good enough so you can actually study the details of the Lyman alpha emission line. So you could see if there's like small peak separation, if there's 2 peaks. That's a good indication that the H1 is thin enough for some ionizing flux to escape. Or if you see the central peak, like in the case with the sunburst galaxy. And the emission flux line ratio, you could get, so this you would get in the visual arm typically, and this you would get in the IR arm. So these lines are typically very, very bright. So it shouldn't be a problem at all with reasonable exposure time. So 1/2 to 1 hour max. And then the slope of the UV continuum you would get in the UV vis channel, and Balmer emission lines again in the IR channel. So you would get actually all of these interesting physical diagnostic in one shot, which is something today you can only do with something like XSHOOTER. So today with alphas, basically what we do, we use GRISM-4 because a priori we don't know exactly what the redshift is. So just to cover as large a wavelength range as possible, use GRISM-4. And then we get a low resolution spectrum. We can get the redshift, and we can measure whether there's strong Lyman alpha. We can measure the equivalent width, but we cannot really see any structure beyond that. If the source is really bright, we might actually see absorption lines as well. So then, in that case, we would sort of have to pick the ones which look the most promising, especially the one with strong Lyman alpha. Follow them up later with different telescopes, maybe even several different instruments, like with Magellan, which we have access to. We could use FIRE in the infrared and then MAGE in the optical for spectroscopy. But it would be quite a bit of work. So, but with NTE, we could actually sort of much easier filter these candidates and find the ones which are really, really good and follow those up. So we sort of tried as a pilot to do this with XSHOOTER. So we got a poor weather program with basically, getting the time that nobody else wants. So 2 arcseconds saying we had up to 4 arcseconds. We still got useful data out of that. Lunar illumination up to 70%, thin clouds. And virtually every source got us good data, both with these rest optical emission lines, Balmer lines, and Lyman alpha, if it was either in absorption or emission. So, I mean, if Mikael tells us that, the difference is between a 5-meter and an 8-meter telescope, between NTE and XSHOOTER, and I think we can recover that by having better observing conditions than this. And this program was like 2 times 15-minute exposures. Not that deep. One of these lenses was pretty cool. So this is again at redshift 3.something, 3.29. So we got quite fast-track observations with NOT, because this was interesting both because of the source. It was the brightest we had found so far anyone had found at that redshift or higher, but also because of this lens, because it's at redshift 1.335. There are not many strong lenses known at that redshift, and particularly not with such a large Einstein radius. So this is 18 arc seconds. So here's the HST image we got. Yeah, it's a really rich distant cluster. Of course, there are not expected to be a lot of clusters like this at that redshift. That's highly unusual. Okay, conclusions. So NOT has proven to be a very efficient telescope for a confirmation, redshift measurement, and some initial physical characterization of these new lens sources. And we can select the most interesting to be followed up with the larger telescopes. But I think that the power of NOT, particularly for finding these leaker candidates, would be a lot enhanced with NT. So looking forward to that.